Hello, my name is Elie El Khawand. The topic of our discussion here is the MIPS pipeline hazards. This presentation has been developed for a project at the American University of Beirut under the instruction of Dr. Ali Chehab. The objectives of this PowerPoint are as follows. First, we will define hazards. Then we will introduce three types of hazards. And last, we will tackle ways in order to design a MIPS pipeline correctly to be able to overcome these hazards. So what are pipeline hazards? So hazards are errors that could occur in a MIPS pipeline due to the dependency of some instructions on the previous instructions that are currently being executed. In this presentation, we will tackle three different kinds of hazards: structural hazards, data hazards, and control hazards. In addition, I will provide real-life examples in order to better understand the problem at hand. So first, we will start by structural hazards. For that purpose, to better understand structural hazard, we will discuss the conversion from a non-pipeline fashion into a pipeline fashion using the wash and close example. So whenever person A finishes from the first stage of the pipeline, which is here, for example, wash and close, B could use that first stage while A jumps to the next. When B finishes from the first stage, C can use that first stage while B uses the second stage drying, and while A uses the third stage, which is folding the clothes. Now, what could happen if person A and person B really need to use the first stage, which is the washing stage, at the same time? This will create a structural hazard. MIPS pipeline. Okay, in our MIPS pipeline, if the instruction memory and the data memory were really located in the same place, and if an instruction really has tried accessing instruction memory and another instruction tried addressing data memory, and these both two memories are actually at the same location, this will create a structural hazard. And this was the main purpose of splitting the instruction memory and the data memory. Now, moving on to data hazards. So data hazards are hazards that originate due to the dependency of some instructions on other instructions to be executed. In this case, we can really stall the pipeline in order to finalize the execution of these instructions before other instructions are executed. In order to better understand the problem at hand, we will consider the problem, do I have diabetes? So we really need to know the fact that someone is considered diabetic, or to be more scientifically correctly, someone is considered to be hyperglycemic if blood glucose level is actually above 125 milligram per deciliter. For that, we'll translate the following pseudocode into MIPS. The number would be actually our glucose level located in S1. The constant 125 is actually located in an array of constants located at $T0. So its address is found in $T0. And the 125 is actually at the first index. So we need to load that and then subtract the current value of our blood glucose level from 125. And if this number is greater than 0, then we have diabetes. And it is important to note that, for the sake of this explanation, that $0 is actually, before loading the 125 in it, actually has a value of 0. So for this following code, when the subtract instruction is to be executed, the S0 would really have the previous value in it, which is 0. So this is actually 0. Why? Because for S0 to be updated, this whole instruction needs to be finalized. However, this instruction is actually executed before this first instruction is finalized. So S1 minus S0 would actually be S1. And comparing S1 to 0, that would actually be a positive number because our blood glucose level cannot go negative. And comparing that with 0, it will always be greater than 0. So for this code, we will always be diabetic. So a possible solution could be adding several no-ops between the instructions in order to finalize the execution of every instruction before the execution of the other, especially that this instruction really relies on the value of S0 that needs to be updated from this instruction. And so to better solve the problem at hand, we have introduced the concept of forwarding by introducing several registers after each stage. And so for our case, the load word instructions would have the value of S0 only after data memory access. And so S0 will be stored in this register and can be forwarded via the forwarding unit from this register back into the ALU. And so because there is still one clock cycle difference between these two instructions, okay, we will introduce a data hazard detection unit in which it will stall the pipeline for once now before the next subtract instruction is executed, minimizing the stalls from 2 to 1. And in some cases, we really could eliminate the stalls. For example, if we have an add instruction and another subtract instruction that rely on each other, let's say the common register is S1, S1 after the add instruction will be located in here, and therefore it can be forwarded back into the ALU in order for the next instruction, which is a subtract instruction, to be executed, and here we'll be eliminating all the no-ops. So this would be really a summary of our new pipeline after introducing the forwarding concept, eliminating the 4 no-ops to only 1 no-op. Next is control hazard. For this type of hazard, we will focus on the branch instruction. We really know that for that branch instruction to be executed, this whole instruction needs to be executed as it relies on the value of S1 computed in this instruction, and this whole instruction needs to be executed before knowing to branch or not. So we have here double the delay. So in order to possibly solve that, we will use the forwarding concept from the execution stage of this instruction and forward it to the ID stage. Now, why the ID stage is that we have moved hardware into the ID stage to really faster, to make this process faster of branching or not. Now, to better solve the branch problem, we will consider the one-bit predictor. So whenever the branch instruction is to be executed, we will check that one-bit predictor. If it is 0, then we will branch diabetic. If it is 1, we will not branch to diabetic. And then when the whole instruction of the branch is completed, we will compare what has been taken and what the real thing is to be taken. And if there's some error, we will flush the pipeline. Now, how do we update this one-bit predictor is based on the previous finding and the previous samples that are taken and whether branching to diabetic or not has been done.